Yeah, maybe let's just start.
Okay. Okay, so this and today and tomorrow, I'm going to talk about this cutting algorithm. So let me say that this part of cutting algorithm today and tomorrow is to a large extent is independent from what you heard on Tuesday and Wednesday about this derivation of the cumulant formula. So this is essentially two independent parts of the proof. I mean, there is only one thing we need to take from yesterday, that is this formula. So let's start by recalling. I mean, there is a lot to recall, and because we need to be sure we are familiar with the setup, so let's spend some time here. Okay, so the EH, remember this is a cumulant, at time L tau is equal to sum over m and belongs to star IM. Okay, so this is the formula we need to take from yesterday. But of course, we need to explain what this M means, what this star means, what this IM means. Okay, so first of all, M. So M is a molecule. And the molecule we know is essentially a topological reduction of the actual particle trajectories, which means that we only care about the particles, the trajectories, and the collisions and their relative ordering on the particle trajectory, and do not care about the exact position and velocity and any kind of exact parameters. Okay, so we'll have a different point of view of the molecules later, but for now, let's see a molecule which is equal to topological reduced particle trajectory. Let's see, a molecule looks like this. So having a... Okay, so by the way I draw molecules is a little bit different from what Xiao did. So he usually doesn't draw out this node here explicitly, and he draws something like this. But it's equivalent because I want to emphasize the fact that we are having an object, a collision here, indicated. So I'm indicating this by a node. But okay, so this doesn't make a difference like this and this. Okay, so this is a molecule, example of a molecule. So by the way, there are also the so-called overlaps. Like sometimes we may represent overlap by a kind of a fully dotted node, but in our argument we'll essentially kind of ignore the overlap. So the overlap will not play a kind of big role here. So let's just think of this as collisions. Okay, so let me say these are the atoms, or we call nodes, which represent collisions. Okay, and these are the edges, which represents basically the straight lines. Remember, for each particle, between two collisions, this particle is going in a straight line. Okay, so there is a fixed velocity v and the position x. At the beginning and at the end, that just goes linearly. So basically, between two collisions, each particle goes in a straight line. Okay, and this is represented by this edge. So this edge is the trajectory of this particle between these two collisions, and this is called, we are also calling it bonds because it connects two atoms. But then also these edges, essentially, which we call the ends, which this represents the part of the trajectory of this particle before the first collision. Okay, so before this collision, there's no collision at all, so this we're calling this an end. Okay, and similarly there is this, which is an end, which represents the trajectory of the particle after its last collision. So after this, there is no more collisions, it's just going in a straight line. Okay? So this is what we call a molecule. So we see at this time it's still a topological reduction of particle trajectory. It is still kind of intimately linked to the particle trajectory. But later on, once we start defining the cutting, we'll change our point of view and we'll think of this molecule completely as a graph-theoretic object. So we'll not link it with actual particles. For now, let's still think of it as this. Okay? So let me know if you have any questions. But this is a molecule. Now this is M, and what is a star? So we also explain what is star. Star is a set of molecules satisfying the following properties. That M is formed by L layers, and each layer is a tree of size less than, let's say, log n to the c. Okay, so in practice, this is a simplification, but I think let us keep ourselves in the simplest case. In practice, this each layer will be a Fourier, so even with a little bit of cycles, but this only leads to kind of non-essential complications, so we ignore it, and let's think each layer is a tree and of this size. Okay, and second, for each layer, L, let this RL set of crossings between layers L and L plus 1, then each such crossing is connected to another crossing via layers L and below. So this needs a careful explanation. So let me say that this is the most important property we'll use for the molecule, and this is kind of the main reason why we can have our good estimates on molecules. But let me explain what this means. First of all, what is the picture of molecules? So let's see. We have many kind of layers. So let's say we have okay. So let's say each layer we have a tree, and moreover, the thing is about so what is a set of crossings? A set of crossings is basically an edge that crosses. So this is 0, this is tau, this is 2 tau. Let's say this. So L is 4 in total, 4 layers in total. Okay. So the crossing means you are having an edge here. Okay, essentially crossing the the layer below L, below this line, and layer above this line. So this is layer 3, this is layer 4. So this is crossing between layer 3 and layer 4. And there are many, there are many crossings like this. Many crossings like this. Okay, so let's show one more. Okay. And the set of crossings at layer 3, between layer 3 and layer 4 is called R3. So this is like R3. And then you see there are also crossings here. Crossings. This is R2 and so on. Okay? So this property is saying that each crossing, let's say we look at each crossing, in R3, so each such crossing, it must be connected to another crossing via layers L and below. So this is layer 3, so L equals 3. So let's say we look at the crossings in R3, so each of these crossings, so each of these edges is connected to another edge, another of these edges via layer 3, layer 2, and layer 1. Okay, so let's see. Let's ignore this for now, but the thing is, it could be possible that this is directly connected to this. Right? In this case, these two crossings are connected, and it may be directly connected here. That's also possible. But it's also possible that they are not connected in these layer 3. For example, they are connected, here. They're not connected in this layer, but then it enters this layer 2 and then they get connected. Like something like this. This is also possible. Okay? And then it's also possible like if they, and of course before connecting they also branch. Branch like this, and then they're still not connected, but let's say when you enter layer 1, it finally gets connected. This is also possible. Okay, so the only requirement here is that each crossing at layer L must be connected to another crossing if you count all the layers below it. And what does this mean? In terms of the particles and trajectories, this simply means, remember, each crossing means a particle here. So there is a particle here, and there is a particle here. And all these particles, the fact that they cross this layer means that they must contribute to the cumulant at time L tau. So if they contribute to a cumulant, that means they cannot be independent from the others because cumulant contains captures those particles that are not factorized. So they must not be independent from others, and then they must be linked to others. And by linking, we mean that they must eventually be connected, to some other particle here by collision or sequence of collisions or all kinds of a set of collisions. Eventually, by going backwards, kind of backtracking below. Okay, so is there any questions about this part? Okay.
Is this condition coming on because you are extending this layer by layer?
Yeah, so because each time we are dealing with the cumulant. Cumulant means the condition of the cumulant forces that each particle must be linked to another particle kind of below, and this translate, just word by word translate to this condition. Yes?
I want to ask, in the first 0 to tau, are there allowed to be any free end?
In 0 to tau, here in this layer?
Are any free, so you have some branching, right? So
Yes.
are any branching without any end allowed?
Without, what do you mean? You can have a free end here. You can have a free end that goes down here.
Okay.
That's what I mean?
Yes, this is allowed.
This is certainly allowed, yeah. Okay, so this is a condition, and this is so we'll draw more concrete pictures about molecule, but this is essentially what it says. Like let's look at L equals 3. Each of these must be eventually connected to another. And by the way, so a good intuition is that each such connections will lead to recollisions or cycles. The reason is that if you look at this layer is a tree. So these crossings, they must be connected somehow. Actually, they must be all connected somehow within this layer. And then let's say if these two specific crossings that are connected below, that are connected above, then you get a cycle. You obviously get a cycle in here. You see by following this, you get a cycle. And if you have many of these particles connected to each other, then you do get many cycles. So basically, the thing is that it turns out that the number of recollisions of picture is as many as the size of these crossings are. So we actually use this as in the later on in our proof. So,
excuse me, you don't take into account the sign of in the definition of E of this trajectory or not?
Here, you mean there is a sign here?
Yeah, no, I mean, when you expand E, you have something which is not all terms are positive. Some are positive, some other are negative. Right?
Yeah. So there are signs here, but in the estimate, like we are just using triangle inequality to bound this individual. We don't, in this part, in the estimate of the cumulative, we don't care about signs. In estimates of the Boltzmann, we do need, but now we don't. Okay.
So do you assume the tree in level L, a connected tree?
It is a connected tree. Each layer is, in practice, it may not be connected, but we have a bound on its number of components. So just let's keep ourselves in simplest case and let's assume they are true. Okay, so we explain what is M, what is this sum. Let's explain what is IM. IM. So let me first copy down what Xiao wrote last time. Essentially, it is epsilon to the minus d minus 1, and let me call it P over R set times this integral. And then we have S M, M of indicator M times initial data. So initial. Rather, let's say the product P F F A of X P V P, and then we have the product P B. Let's call it J. Okay, so the reason I'm writing this here is because I'm not going to use this formula, and this basically means this is just a normalizing factor, powers of epsilon coming from the expansion, and this Sm is basically the change of variables, the substitution that associated with the collisions happening in this molecule M, and this is an indicator function that all the collisions in this molecule M indeed happens, and this is essentially the initial data, and those factorized parts where Fa is approximate solution to the Boltzmann equation, and this is just basically for each particles you have these variables Xj, Vj, which you're integrating. Okay, but this is. Let's ignore this. This is basically means that it's a renormalized, normalized probability that all the collisions in M are happening. So I think it's really the L1, but let's forget about this technicality. Let's just imagine this is IM. Okay, so the thing I'm talking about now is that this is going to be reduced to a kind of a more kind of systematic notation. Essentially, if you look at this, the thing is that this Sm involves a very complicated change of variables. The change of variable is a composition of all the change of variables associated with all the collisions happening in molecule M. You can imagine this is extremely complicated. So we don't want to keep this complicated thing here. So the thing is that we have, so I of M, or rather I of M in L1 norm. Okay, so there is a power of epsilon. Okay, so never mind, I'll explain what these are. But then the thing is that this is integral. Okay, so we have a product in N. So this is a formula that we'll actually use for this IM. And now let me explain what each of these objects is and what is the intuitive picture. how do we link, this probability to this inequality. Okay, so let me. So first of all, E is a set of all edges in the molecule M. Remember, molecule has these edges, which includes the bonds connecting two atoms, and the ends, which just go freely from one atom. And the M, of course, is a set of atoms in M. So the size. So this means that the size of the number of total edges, and this means for the number of total atoms. And then in fact we have, and this is a pretty elementary fact, just proved by simple counting, that E minus 2M is equal to this set P minus R, I think plus the set of the cumulant H, but this is not important. So basically, if you ignore this, then you see this is equal to this. So the formula here, this factor corresponds to this factor. Okay, so this is not very important, but it's important to keep in mind of this these coefficients, because we'll see this later. Okay, so this first thing, and then we're having this huge integral for each atom n. So n is an atom, which represents the collision, remember. For each atom n, which is a collision, this Tn equals a time, collision time for n. So it's a variable, it's a time variable. We're integrating in that variable. You see, we're integrating in dTn. Okay? And moreover, we have this delta n. What is delta n? This delta n is a delta function that represents the exact collision happening at the end. So delta n is this. So let's say we have n. So this is n. This is atom. Okay? In the molecule, it's n. And it has two edges going down, E1, E2, and two edges going up, E3 and E4. Let's assume that E1 and E3 correspond to the same particle in the collision, and E2 and E4 correspond to the same particle. So these particles collide, and one goes through E3, one goes through E4. And then what is this delta n? This delta n is, the exact formula is complicated, but I don't need to write it, but it's very intuitive. It's a delta function of VE3 minus VE1 plus VE1 minus VE2 dot omega VE4 minus VE2 minus VE1 minus VE2 dot omega delta of XE3 plus Tn VE3 minus X1 minus Tn VE1 delta of XE4 plus Tn VE4 minus X2 minus Tn VE2 times VE1 minus VE2 dot omega to the negative times delta of XE1 plus Tn VE1 minus XE2 minus Tn VE2, where omega is 1 over epsilon times this vector XE1 plus Tn VE1 minus XE2 minus Tn VE2 belongs to a unit vector. Okay, so this is wrong, but let me explain. This is very intuitive. Let me explain what this means. Okay? So, remember, for each atom, each node, each atom, means is a collision, and then each edge, which is either a bond or an end, each edge means a linear piece where a given particle travels linearly. So if the particle travels linearly, there is a unique velocity, unambiguously unique defined velocity. So if E is an edge, then VE equals the velocity of the particle at E, a particle at E. Okay, and what is XE? So since in this edge, this particle is traveling linearly, then if you transport back this particle to time 0, then there is an unambiguously uniquely defined position. If your particle starts at that position, at time 0, then it will get to this position and this position, in this time. Okay, so XE equals time 0 backward transport of this particle. Unfortunately, we have to do this backward transport because otherwise we cannot define the variable XE unambiguously. And so as a result, if you look at things like XE plus TVE, and by the way, if this is n, then the Tn is the time of these collisions. If you look at something like this, XE plus TNVE, that simply means the position of the particle at the time of this collision, because the collision time is Tn. If you transport back to time 0, you get XE. Then if you transport backwards, transport back to this time Tn, you get XE plus TNVE. Okay? So this just means the position of the first particle at this collision. And what this means? This means the position of the same particle right after the collision, because this means the position of the particle right after the collision, and this means the position of the same particle right before the collision. Okay, and we know they are equal because the collision doesn't change the position of the particles, and so this delta function simply restricts that. We are respecting the rule of collision. That is, collision, the same particle, it doesn't change its position after collision. Okay?
Excuse me. Here, your XE means like something like the pre-collision velocity. Position. It's not like really going all the way back to like time t equal to 0, right?
So this is like you go linearly backward to time 0. So it's like you talk about the position, not position at this time because it's not ambiguously defined. You need to go talk about the position of the particle at time 0 if it was transferred linearly.
So as if like nothing happened before and you just
Yeah.
Okay, thank you.
Okay, so then this explains this term, and this term is the same. Okay, this term is the same. And then of course, what about this? These are just collision rules. The output velocity is equal to this formula. You can recognize the collision formula. And again, this is the collision formula. And this is a weight which naturally occurs, and this is really just a restriction that this collision happens at all, because at this time of collision Tn, the distance between these two particles is exactly epsilon. And finally, this omega is the same omega that occurs in the collision function. So you see, really, this delta n is just an exact delta function that indicates that this collision happens. And then if we integrate all these delta n, take product all these delta n, then we know that this is just a indication, just a way to express that we have just this equivalent way to express that we have all these collisions. Okay, so this is, we said this, and of course, X, E, and V are as this. And then, so we explain what delta n is, the X, V, E, and T, N. And this FA, you can ignore. It's essentially just the initial data and those data that are factorized. So FA equals approximate solution to Boltzmann. And then, applied to E, which are bottom ends. Let me explain what is bottom ends. A bottom end means that if you have this atom, a collision, and then this is the bottom end. Bottom end means that for this particle, there is no collision below this E. So E is the kind of the part of this particle before the first collision. So this is before the first collision of a particle. So in other words, this is the first time where this particle enters the whole picture, and it has no history, and this is the starting point of its history. Okay, and of course, this particle enters, when it enters by this factorization Fa, and there is no history of the particle before that, and we simply just corresponds to this E. Okay, so this is the initial position velocity. Okay, but in practice, this Fa factor can largely be ignored because it's just bounded, and we can treat it as 1 as long as we can bound each of the XEV variable in a compact set, and then we don't worry about it. So the important thing is this delta n. Okay, so we need to find a way to integrate this delta n in those variables. Okay. So this is explanation. Now we have explained what are these. This EH is equal to sum. So we explain what is M, what is star, and what is IM. Okay. Before we proceed, any questions about this part?
Tn started from which time point?
Yeah, good question. So Tn depends on the layer. So actually, here let me just remark that. If an atom n belongs to basically L's layer, then Tn belongs to L minus 1 tau and L tau. And so in particular, each Tn belongs to an interval of length tau, which is much less than 1. Okay? Any other questions? Okay, so now we have this formula, which is essentially the only thing we need for the lectures today and tomorrow. And now, before we go to the definition of cutting and the cutting algorithm, let us just make sure of one thing, that our goal is to estimate the L1 of EH, which is a sum of the L1 of IM, and L1 of IM is written down here. Okay, and then to estimate this big sum, we need to estimate two things. The first is the number of terms in this sum, and second is the size of individual terms. And let me write down the two estimates for this. So actually, let me keep this and erase the rest. Now, okay, so we have one is less than okay, so this is triangle inequality, clear enough. Okay, so we need to estimate these two things. And just for simplicity, because we're estimating the L1 of IM, and it is a L1 of IM that has this nice integral representation. So for the rest of the lecture, let me just abuse a little bit of notations and just call this IM, this L1 norm to be IM. Because, it's really this quantity we are looking at. So just, okay. So then we have the claim. 1 is a number of molecules is less than c to the m times log n to the c rho, where c is a constant. M is the number of molecules, number of atoms in the molecule M, which is number of collisions, or equivalent number of particles. Each trial on average will have 1 collisions. But okay, so number of atom, number of collisions, and the rho is the total number of crossings, which is let's say the. So if you still remember, this RL is the set of crossings between layer L and layer L plus 1. These yellow edges is R3 and RL is similarly. And rho is the total number of crossings, which is the sum of this. Equivalent, you can also think of the maximum of this, because in our treatment, we're always treating the total number of layers as a large kind of an absolute constant. Okay, so this is the first thing. That, yes? Okay, that if you have a molecule with a total size of little m and the total number of crossings being rho, then the number of such molecules is always bounded by c to m times log n to the constant times rho. Okay, so let me first prove this, and then we will get to claim 2. Claim 2 will be the estimate of this I, which is a core of the proof. Okay, so let me keep this picture for a while. Basically, let me prove. We draw a molecule M by first drawing a tree in each layer. So if you look at this picture, in each layer we have a tree. So if you just restrict to each layer, ignore all the other layers, we just get a tree. So of course we're drawing, to draw the whole molecule M, let's say we first draw a tree in each layer. Okay? Then we connect the trees in adjacent layers by joining a top kind of a top end and the bottom end. Let me show you how this works. Okay? So do here is that let's say you draw, let's just think of 2 layers. The multi-layer case follows in the same way. Let's say we draw a tree like this, so whatever you like. You may have branches, okay, and draw a tree on top layer. Let's say we draw a tree in the bottom layer. Okay, so let's say we draw this corresponding this. So something like this. Okay, so how do you combine these to get the whole picture? What you do is that you just choose any set of atoms, and then you draw. You kind of, let's say you choose this. Let's say you choose this, and then this. You join it to make it an edge, and this edge will be a crossing. It will be a crossing between the upper layer and lower layer. Okay? You join these two ends to create a crossing, and the same way you can join arbitrary, kind of join these 2 ends to create a crossing, you can join this edge, this end to create a crossing. This can be done completely arbitrarily, but then the number of crossings is limited by this RL. Okay? So basically, by doing this, you can get arbitrary molecule M by first drawing the trees and joining the ends. And now let's count how many choices we have in the first step, how many choices we have in the second step. And this is simple because if there are ml atoms in layer L, then the number of choices for the tree TL is less than a constant, let's say 100 to the ml. We don't need 100, maybe 10 is enough. 10 is more than enough, I think. So this comes from a combinatorial fact that if you think of the number of trees, with a given, because TL is a tree, TL is a tree, and moreover, the degree of each atom of TL is at most, is 4, or let's say at most 4, because if you think of the bonds, because if you have a tree like this, okay, so each atom is having at most 4 edges. I mean, some of them must be n, might be n, might not be connected to something else, but the number of bonds, number of connections is at most 4. So because the number of trees of, let's say, m nodes and the maximum degree less than 4 is bounded by 10 to the m. And it's a simple combinatorial fact because every such tree, you can think of it as a ternary tree, and the number of ternary trees is well known to be exponentially growing in the number of nodes. So I'll now explain this. So basically you do some generating functions and you are good. Okay, so by the way, this is not the number of all trees. The number of all trees is factorial, but the number of trees under this restriction is exponential. Okay, so this is the first thing. So to draw this tree TL, you have these 10 to the ml choices, and the sum of ml is equal to n, which is the total number of atoms, and then we get to the choices for step 1 is less than c to the m. Okay. Now what about choice 2? Choice 2 is even easier because you just look at each layer and you join these layers. You can choose arbitrary ends to join, but then the total number of ends you have at all is bounded by a power of log n, because the total size is bounded by power log n. So in second step, number of choices is less than log n to the c. Okay, so let me say the product. To c to the RL, because you exactly make these RL number of new edges, and each new edge has a log n to the c choices, and then by the multiplication principle, this is the product of all this, and this is less than log n to the c times rho, where rho is the sum of the number of crossings. Okay, so is it, yeah?
So in every layer, the size is log n.
The size of every layer is bounded by log n. This is a kind of
And for every crossing, I choose two points.
Yes, log n square.
But then I feel that you have like L layers. Why this L then?
L is not a constant. L is if you put L here, I mean it's fine. So like L, we always treat L as a constant. So you can think how L is allowed to grow its n, but let's forget about that. Let's just think L is a constant. Okay? Yeah. So because for example, this will be we think the maximum of RL is comparable to the sum of RL. We're really treating L as a constant. Okay. Okay. So
If you don't do the layers, Just the root about the tree.
But the whole thing, if you put all layers together, is not a tree because it's having longer cycles.
I see. That's the
Yeah.
layer.
Okay, so now we have claim 1. We proved claim 1. Now let's turn to claim 2. The claim 2 is basically saying, let me erase this picture. I'll draw a more precise picture later. So
can there be cycles inside the layer?
there cannot be. I mean, in practice there can be, but in the simplified model there cannot be. In practice there can be layers inside cycles inside layer, and we need to do some procedure to remove it, but it makes things more complicated. So let's look at this simple picture where each layer is a tree.
In our paper, there is some small amount of cycle in each layer, but it's small and will be known as a department.
Okay, so now let's turn to claim 2. Okay, so this is our claim 2. That the size of this IM is bounded by tau to the m times epsilon to the c rho. So here c is a small constant, positive constant, and this m is the same as this m here, and this rho is the same as the rho here in claim 1. Then from here, obviously, you see that if you multiply this, you get c to n times tau to m, and since tau is being small, c is absolute constant, this c to n is apparently killed by the tau to m, and if you have log n to the constant multiple constant times rho, and you have epsilon to the 0, remember n and epsilon related in a polynomial way, then again this log n to the 0 is going to be cancelled by this epsilon 0, and if you sum up all the m, you get convergence. Okay, so this and claim 1 implies the desired bound. So for the rest of today and tomorrow, we're going to focus on the proof of these claim 2. Okay, and let me make one remark about the 2 factors in claim 2. So why do we have this tau to m? The reason I said is that, I think I erased it, that each time variable, this is because each time variable, the n belong to time interval of length tau. Okay, it's always a time interval length tau, and then if you integrate in all the time variables dtn, remember we're integrating all dtn, we automatically get this tau to m. And this kind of, we always get it for free. So let's not worry about it, we always get this. The important thing is to get this power of epsilon.
Excuse me.
Yes.
The dependence on L, on the number of layers,
Yes.
is where in this formula?
There is no dependence on L. I mean, you know, there are C. There are various big C's. These big C's may depend on the total number of layers, big L, but it's a constant. Okay, and this little c is a constant. This little c will also depend on L. So this little c will be like 1 over L to the 10, but L is treated as constant.
So basically, time is arbitrary but fixed.
Fixed, yes. So if you really want to investigate the dependence, I told you the answer is this big L can be log n to the 1/2 somehow. But let's not worry about that. Okay. Okay. So now the question is how do we get this? And this is where we need a cutting algorithm. So before we introduce the cutting algorithm, let's first recall the notion of cutting. Let me say that to get the crucial epsilon to 0 factor, we need to do cutting. Okay, so how to do cutting? Let's just look at one example. Let's say this. Okay, so this is a part of the molecule. So these things you can have further connections up, have further connections down. It is not important. Okay, so let's see if we cut. We do a cutting, along this line. Then what happens is that it turns into okay. So let's further assume that the top one is cut as free, the bottom one is cut as fixed. This is artificial, and then we have this. Okay, and moreover, we think this as we put a little cross here, indicating that this is fixed. So this basically is what we call free end. This is what we call the fixed end. So basically, the only thing is that we cut this edge, this form, okay, into one free end and one fixed end, and we can choose the up one is up part. The top part is cut as free, so we put the free end here. The bottom part is cut as fixed, so we put the fixed end here. The fixed end is indicated by a small red cross. Okay, so this is the cutting. And what this mean? What does this mean in terms of estimating this IM? And this is also clear. I mean, basically the thing is that when we have an edge being cut into a free end and a fixed end, remember this edge is associated with a variable, ZE, which is XE and VE. Okay? So when we cut into free end, so this is a ZE, and this is the same ZE. So basically this variable is the same as this and the same here. Okay, so what does it correspond to in terms of the integral? Basically, schematically we think that IM is an integral of whatever things, and then we have the product of D of all vector variables, the ZE variables. Okay, so this whole thing is M. Let's call the fixed thing being M1, the free thing being M1, the fixed thing being M2. Then what we do here is really just write the full integral, writing the full integral in terms of iterated integrals. So this is equal to integral of product D ZE variables in M1, and then product D of ZE variables in M2. So in other words, in this integral, you are first fixing those variables M1, that is, you fix this ZE, okay, and then you integrate in those variables M2, and when you integrate M2, this ZE has been fixed, so that's why we call it the fixed end. So this has been fixed, but you're integrating, in the rest of variables, in these variables only, okay. And then once you finish this integral, and then you go back and you integrate M1, and now it is the free end because this variable is integrated when we deal with M1. So the whole thing is really just an iterated integral, and from this we easily get this bound that. If M has fixed ends, in the beginning, the n has no fixed n, because in the beginning there's no cutting, so it has no fixed n. Then define, so Im is a soup of Ze for all fixed n's. Integral of exactly the same thing we have in definition Im. Unfortunately, I have to erase it, but exactly the same delta function, whatever. Products when integrate on bonds plus free ends dZe. Okay, so you only integrate in the bonds and free ends, you ignore the fixed end, but then you take the supremum in all the fixed ends. So if you define Im in this way, then if m is cut into m1 and 2, then Im less than Im1 times Im2. Well, this follows from this iteration, and then you bound, for each fixed value of these variables, the second integral is bounded by Im2, and then you integrate back, you get Im1. This is okay. So I think the first half of today will end here, and in the next hour, I'm going to talk about this. Using this, I'm going to introduce these elementary molecules, and then we lead to this discussion of the cutting algorithm.
Any questions? Yeah, maybe we just have a tea break. Yeah.
Okay. So let's start from here. This is inequality where we after cutting, and then we can keep doing cutting multiple times, and then if we cut, into m1 to mk, then Im is less than the product mj. So in practice, we're going to cut m into one of the following kind of 4 types. Define the so-called elementary so there are these degree 2. So let me call this degree 2, which so let me make 2 remarks. So first of all, when we count the degree of the atom, the fixed ends do not count as degree. So only the free ends and the edges, the bonds, are counted as degree. So this is just our special notation about degree. So this atom will have degree 2 because it has 2 fixed ends, and the other 2 count as degree. So this has degree 2. This first remark. Second remark is that for degree 2 atoms, we only accept this case and this case. We do not accept if you have one top fixed, one bottom fixed end. The reason is that if you integrate the delta functions along this atom, you get a singularity, you get a delta function which you don't like. But when you integrate the delta functions, along these and these atoms, you get a constant, you get an indicator function which is bounded by 1. Okay, so remember we don't like this. So this is actually one of the important properties we'll need to keep in our algorithm, but that's for later. For now, we just introduce this definition. This is degree 2. And degree 3 is just you have only one fixed end. Let's say this one can be anywhere. This or any others. The fixed end can be here, 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 here. It's completely symmetric. This degree 2, degree 3. And then we have degree 4 with no fixed end at all. So just degree 4. And then we have degree 3, 3, which contains 2 atoms. And there is exactly one fixed end at each atom. So this, and again the fixed end can be anywhere. So either here or here, or here. Sorry, this cannot be. It has one fixed end. Or here, or here, or here. Anywhere it's fine. It's called 3, 3. Okay, so this is called 2 atom, 3 atom, 4 atom, and 4 molecule and 3, 3. And the thing we are going to calculate, we're going to perform a cutting operation that cuts our molecule into a number of different, each one being either this or this or this or this. And then by this inequality, let's just bound the estimate, the integral of the I and j, and we can easily calculate it. For any 2 molecule, so this is less than 1. Well, the reason is that, if you integrate that, you integrate delta function, and delta function exactly cancels with the integral, you get an indicator function which is just size 1. And then this. In fact, you can just do a calculation. You integrate in this variable, you get the power epsilon d minus 1. But if you follow the definition of this I, you have in front your negative power for epsilon, and this exactly cancels, and you get again like the 1. And this is a bad case, a degree 4. If you do the same thing, you integrate, the integral is still size 1, because this integral is 3, you can fix them, you can integrate them arbitrarily, and the rest has epsilon d minus 1. But then if you compare with the negative power of epsilon in front, you are getting a negative, epsilon to a negative power in total. And this is a bad case. And finally, this is a good case. It's a positive power of epsilon, and the reason precisely is that you are having if you after you integrate one thing, you're going to have this other condition indicated by the collision, and then it gives you an extra power here that we explained in the beginning. Okay, so I'll now explain the proof of this. These are elementary estimates because you have finitely many edges. You just plug in the definition of the integral and you just really integrate that. So there is nothing nothing illuminating in the calculation. So let me just keep this. The important thing is that once you have this, then epsilon to the sum power, what power, is basically, like a number of 3, 3 minus d minus 1 times number of 4. Okay, so this is obvious from these 2 formulas. And then recall our goal. We want to bound this ion by absolute 0, and we just need to show that this thing is bigger than a constant times 0. So we have the goal. Let me write it here. Objective. Cut M into elementary molecules such that the number of 3 3s bigger than little constant c times rho, the number of degree 4 is less than, so some constant times number of 3 3. And once we have this, we'll complete the proof because of these estimates. Okay, so this is our objective, and for the rest of today and tomorrow, we'll be focused on completing this. So basically, there are 3 things we need to do. Let's keep in mind this. It's just heuristically. So things to do. Make sure there is no, bad, so-called bad degree 2. Bad degree 2s, and this will be guaranteed by something we call monotonicity property in the cutting sequence, which we'll explain later, but this is some objective we should keep in mind. And then we should minimize number of degree 4, because this is the bad thing. This is where you have the negative power here. And then maximize the number of 3s. Okay, of course, this is not easy to do, so we'll achieve this by a number of sophisticated algorithms that we'll be discussing tomorrow. For now, let us first look at a very simple case and just have an idea, how this is guaranteed, how this can be guaranteed, and how to just as exercise how to practice the cutting algorithm, how the cutting works. So let's just look at one example, and then we'll see how to do a general case. So let's simple example. Okay, so let's say we have 2 layers, and then we have so each layer is a tree. It's actually a chain, a pretty simple case. And now, let's say we have these are crossings. Okay, so these are crossings. Now, let's say we complete adding the edges. Of course, this chain can be arbitrarily long as you want. So the question is, how do we get many 3 3s from that? And how do we get, few 4s? And this is easy. So let's say we first cut this one. Let's say we cut this one. Okay? So we cut this one, we'll cut this as free. We'll have a degree 4. So these are degrees. These are degree 4. Okay? So we get the 4. And when we cut this one, so let's say we remove this, and in principle, cutting this one will generate a fixed end here, will generate a fixed end here. But then, since fixed end doesn't really count as degrees, so let's just simplify the picture by just not drawing out the fixed ends. So if we cut this here, that means we get this. Okay? Now you see, this atom will become degree 3. Okay? So next, let's say we cut this atom. Now it has degree 3. We cut this. We already have degree 3, fine. And now after doing this, we'll have 2 atoms, this and this. They both have degree 3, and they are moreover connected, which means we can cut them together to produce to produce a 3, 3. So each one has degree 3 and they are connected. We can cut these two together. Cut these two together to produce a 3, 3 component. And then just show. Okay? And then you see after this cutting, these two atoms, again, they both become degree 3. They are still connected. We can keep cutting them, and we get another 3, 3. And then we can keep cutting these two, we can keep cutting these two, and we keep going on. And each step we get a 3, 3. And so then in the end, we get number of 3 3s is equal to the row minus 1, I guess, where row is the number of crossings if you have only 2 layers, and the number of degree 4 is 1, you only have 1 from the beginning. Okay, and this is good because this is satisfied, and we are good. Okay, so this is of course a very simple example, but it shows us, it's as a practice of how we do the cutting, and it shows us, in general, how we get this 3, 3 at least in this example. Okay, so notice that the example has a feature that it only has 2 layers. So it only has 2 layers, but we are already allowed to have a lot of recollisions because remember this picture there, like you have a lot of cycles. You're having a lot of cycles by only having 2 layers. So in fact, the 2-layer case is a case that already encompasses most of the essential difficulties, and so actually we'll, in the main part of the proof, we'll be working with 2-layer case only. So this will be we'll discuss tomorrow, and today, kind of the goal for the rest of the day is we are going to reduce a general multi-layer case, kind of in some sense, to the 2-layer case. So the plan, reduce multi-layer case to 2-layer case. And then, prove two-layer case by developing a number of algorithms. Okay, so this is the pattern. So let's start with the general case. So let's draw a 3-layer case. Maybe we can draw even more, kind of 4 or 5-layer case, and see what's the idea of reducing a 2-layer case. So remember that what is a 2-layer case? 2-layer case is like this. Layer up and the layer down, each is a tree. The number of UD connections, or we call number of crossings, but really the number of an atom in up connect atom in down is rho. The example here, this is up, down, and let's say we have a tree up, we can draw anything like this, and then we have to draw a tree. Okay, so we can draw a tree, and then we can draw the, these UD connections. You can have this, you can have this, you can have this, you can have this, you can have this. And then, let's say, this, this is example of a two-layer case. So we'll talk about two-layer case tomorrow, and today let's see how do we reduce a two-layer case. So actually this is not very hard, but just a formally made, the picture may be complicated, have multi-layers. So let's draw a case of essentially like 4 or 5 layers, and we'll see how it works. So we have the top. Let's say 4 layer. Okay. So the first thing is that remember we have these crossings. So there is a crossing between layers 2 and layer 3 and layer 4, which is this crossing R3 and this crossing R3, this crossing R1. So actually, let me put these together. Let me okay. So we have just formally, if you can draw it. So these are the crossings, in R3, and these are crossings R2. These are crossing R1, and so on. So we'll only draw one of them. We'll only draw the maximum of one of them, because this is the only thing that matters. So we choose L such that this RL is max. So RL, okay, so RL is max. Okay, so we choose a layer. So this will be essentially the highest layer we are considering. Let's say in this picture, let's say L equals 3. Okay, so let's draw out these crossings. We have this. These are all the crossings, crossing between layer 3 and layer 4. Okay? Now, by assumption, each these crossings must be connected to another crossing in layer L and below. So these red crossings, it must be connected to other crossing kind of in these layers, in the collection of layer 3, layer 2, layer 1. So let's ask. So let lambda 3 be the number of crossings that are connected to other crossings in layer 3 only. Okay? So, and by the way, we are here in the assumption assuming that each layer is 3, but in practice each layer may not be a tree, it may be a forest in general. So not necessarily they are just connecting layer 3 alone, but you may need to go down to lower layers to have them connected. But let's say, all these yellow crossings, how many of them are connected in layer 3 only? Okay, so let's say some of them are connected. Say some of them will be connected, they may be connected. Okay, so whatever you may have there. Some of these may be connected eventually, and some of these may be connected. Possible. Okay, so we have this lambda 3. The question is lambda 3 large enough? Okay, so is it enough for us if we just stop at layer 3 and forget about every layer below? So let's ask this question. So, is lambda 3 big enough? Let's say bigger than 10 to the minus 6 times rho. Sorry, let's say we call this R3, which is R3. All these particles, all these crossings. Okay, so this 10 to the minus 6 is an arbitrary number, so you have a hierarchy of numbers. So these numbers these coefficients will get larger and larger, below. But let's say we ask is lambda 3 big? Is lambda 3 big enough? If yes, we choose this layer 4 to be up, layer 3 to be down, and ignore all other layers. Okay? What this means is that they are connected. These things are already connected, so we already have enough number of cycles, and enough. By enough we mean this. It's bigger than a constant times, and because this is comparable to rho, and this is our goal. Okay? Then in that case, you see, if you only think of this as up, this is down, ignore anything else, then you see the up itself is a tree. I haven't drawn this out, but it will be something like this, something like this, and something like this. The up thing will be a tree, the down thing will be a tree, and you have sufficiently many crossings, that is between up and down, and then we're reducing to the 2-layer case. We have up is a tree, down is a tree, and the number using connections is not necessarily rho, but at least bigger than a constant multiple of rho. Okay? And then we are reduced to 2-layer case, because if we can cut these 2 layers along, just take these 2 layers as a subgraph and you just cut it, and the rest can be cut using simple naive trivial algorithm we'll introduce later on, and then we already get enough degree 3, we get a few degree 4, and then we are good. Okay, so this is is lambda 3 big? Now let's say if lambda 3 is not big. If no, then lambda 3 less than 10 to the minus 6 times R3. Fine. But then we look at lambda 2. Lambda 2 is lambda 2 be the same thing as lambda 3. But we allow layer 2. So actually, let's say they are not connecting lambda 3 in a layer 3, let's say. Fine. Let's say they are take up other branches is fine, but then they are not connected to each other, in this layer. And let's say this, you may have this, we have this, okay? The question is, are they now connected if we take into account layer 2? Okay, so let's say they are connected. You know, if they are connected, if they're connected somehow in layer 2, fine. Okay, so they are connected in layer 2. Then what we do is that if yes, then we choose layer 4 union layer 3 to be up, layer 2 to be down. Okay, so actually, you see, in this case, lambda 2 is bigger than 10 to the minus 4 times this quantity, and lambda 3 is less than 10 to the minus 6 times this quantity. So in particular, lambda 3 is very much smaller than lambda 2. Okay, so this means lambda 3, whatever happens in the layer 3 is not important. In fact, by making some manipulations, we can ignore them. We completely ignore them. Let's pretend that lambda 3 is 0. Lambda 3 less than lambda 2. We pretend lambda 3 is 0. Then in this case, you just look at the, okay, you put this as up and this as down. Then what happens here is that the down is still a tree because it's a single layer, and the up is also a tree even though it's a union of 2 layers. It's because these particle lines, they are not connecting layer 3, and so they are not forming any cycles, any recollision. So in fact, what happens is that this layer 4 is a tree by itself, and then you're attaching kind of different trees to each atom of the tree, so to each atom of the tree, and then you still get a tree. So basically, let's draw it in a more careful way. So what happens here is that you're having this. Okay, so then what you will see here is that you're having this. You have these thing connected in layer 4, something like this. So that's not important. Okay, and then so maybe you're here. Okay, and then this is in layer 4 and in layer 3. In layer 3, you're having this. You're picking up these tree structures. Picking up these tree structures, fine. But the thing is that they are not connected in layer 3. Because they are, lambda 3 is 0, let's say, they're not connected in layer 3. So what happens here is that you have a tree here in layer 4, and then for each atom in the tree, you are attaching it to another tree like this. Then obviously you see the resulting structure, the whole structure in the union of layer 3 and layer 4 is still a tree. So the whole thing, which is a tree. Okay, so this is a very important thing, so make sure you understand that. Okay, and then layer 2, the bottom layer, which is also a tree. So we are having this, so these things, these are kind of, let's say, so I think they are connected here, so they are connected here. Okay, and then we are matching them. Okay, which means that these particle lines, these connections, they are connected down in this down layer, and down layer is a tree, and up layer is also a tree, and then we're having lots of UD connections because they need to be connected together. Okay, so then we again reduce the 2-layer case. We set this down to up, set this to down, ignore other layers. And then we are kind of isolating this particular structure, 2-layer structure. And now suppose we have a good way to cut these 2-layer structures, then we can just cut them and cut the rest of the molecule trivially, and then we are done. Okay, so that's what happens. Now, if no, then lambda 2 is also 10 to the minus 4 times R3, but then lambda 1 will have lambda 1. If we define lambda 1 to be the same thing, but we allow layer 1, then lambda 1 has to be bigger than R3. Because everything must be connected by the assumption, each crossing must be connected to another crossing if you count layers 3, 2, and 1. So lambda 1 must be big, and then we do the same thing. We choose layers 4, 3, 2 as up, layer 1 as down, and there is no other layer to ignore, so just look at this, and then the same picture here, except you have one more layers in up, but still you effectively reduce the two-layer picture. Okay, so this is the idea of reduction. In general, I don't want to write down the general form, but it's clear. You choose the layer, the first layer, where the RL is max. So in this case, R equals 3. And then you consider, like these crossings are connected to each other below. Then you consider exactly at which layer below are these, are a significant portion of these polylines connected, or these crossings connected, and then you choose this as a lower layer. So let me just summarize in general. Choose L such that RL is max. So RL bigger than rho. Then choose the highest layer L prime less than L, such that a significant portion of these crossings are connected to each other above, or let's say between the layer L and L prime. Okay, so for example, if L prime equals L, that means these crossings are already connected in layer L, and then we just choose this layer. Okay, and if not, we just choose this max and L prime. And then we set layers L plus 1, L, and all the way to L prime plus 1 to be up, and layer L prime to be down. For example, in this picture, this L would be 3, and this L prime would be 2. So the layers 4 and 3 to be up, layer 2 to be down, and ignore other layers. Okay. So let me say that in practice, since it's slightly more complicated than that, in general, each layer may not be a tree, maybe a forest, so you need to consider how many components each layer have, and more precisely, you need to be careful about these implicit constants here. What do we mean by significant portion? We need to choose a hierarchy of constants, like we do here, 10 to the minus 6, 10 to the minus 4, 10 to the minus 2, and so on. But if you work out everything carefully enough, you're eventually going to get the same result that you can effectively reduce to 2 layers. Okay, and well, of course, if you have something that is already connected in layer above, you need to remove them first. But okay, so let me ignore all these things because we haven't talked about the cutting algorithm yet. But eventually, this result allows us to reduce to 2 layers. So the key idea is really that we need to locate, because the fact that every crossing is connected to another crossing gives us the enough recursions to count all these layers. So then we just need to show to see what is how many recollision, how many cycles occurs in each layer. Like if we go from layer 4 to layer 3, let's say. If you go to layer 4 to layer 3, how many new cycles you have? If you go from layer 3 to layer 2, how many new cycles you have? And so on. And you choose the one that is the most significant, essentially. And then you locate 2 specific layers, and then such that the most of the cycles or recursions are coming from these 2 layers. And then you work a little bit harder. You reduce yourself to 2 layers. Okay, so this is the first important step in the algorithm that allows us to reduce a multi-layer case, so here is a 4-layer case, to the 2-layer case. So from now on, we'll be focusing ourselves on the analysis of the 2-layer case. And let me just, I haven't erased this good. So the 2-layer case assume you have 2 layers up and down. Each layer is a tree. Number of up and down connections or crossings is rho, and again our goal is to perform a cutting such that the number of 3 trees is bigger than rho and is much bigger than the number of degree roots. So I think we still have 20 minutes. Good. So it's where's this? So for the rest of today, let me just explain to you the simplest, algorithm we'll use in order to deal with the 2-layer case. And this is one of the, so basically our algorithm, we have many algorithms, but they will be divided into kind of 2 classes. So the many algorithms we'll introduce tomorrow are essentially kind of variations of these basic algorithm we're introducing today. So this is a very important thing. And let me call this the basic algorithm called up. Okay, so before that, we'll need to, let me first introduce a very naive algorithm, what we call the naive algorithm of up. So and this is a very simple algorithm. It doesn't work, and I tell you it doesn't work, but it will be useful kind of as motivation. It's a very simple algorithm. It has only one sentence that every time we choose lowest atom and cut it, period. Okay, so this is a valid algorithm. Okay, so this is what we call naive up. So every time in the molecule, we always choose lowest. Lowest means it has nothing below it. It has no child. It has no child in the picture, and we cut it. Cut it as free. So what happens with this naive up is that okay. So let me say so. So for the naive up, we know that it preserves monotonicity, which means it never creates any fixed end from above. Okay, so this monotonicity is a big deal. Remember that we are trying to avoid these kind of structures, because this is what we do not want to allow. And in the naive up algorithm, it never creates any fixed end from above, so which means that you'll never have this fixed end here. And then at most you can have is this fixed end, which is allowed. Okay? This is not allowed. Okay? Well, this is very naive. It doesn't work, and I'll tell you it doesn't work, but this does preserve autonomicity. Okay? On the other hand, the bad thing about it is that it doesn't minimize the degree 4. We'll show this through one simple example. Let's say if you have a chain like this, zigzag. Okay, so you can draw it like this, like this. Okay, so if you apply this naive up, so let's say you cut degree 4, lowest, let's say this one, this lowest. You cut this. Well, you can cut this, fine, but you have degree 4, 3. But then next you choose lowest. You see this guy becomes degree 3, but it's not lowest. Lowest is this one. And then if you really do this, you will need to cut this. And this again degree 4. And then you get a 4. And then this guy is degree 2, you can cut it, fine. And then again, this thing becomes degree 3, but this is not lowest, this is lowest. You cut this again, another degree 4. And so on. You keep going, you see you're having a lot of degree 4 in the process, which is something really bad. So that is why this algorithm is not what we actually use it, but it serves as a motivation, like kind of it suggests us what to do, like if this doesn't work. So this is bad. This is bad, but it does prevent these possibilities, these loud possibilities. It doesn't, and not to mention, does not maximize number 3 threes. So this is not very useful. But what is useful is a variant, slight improvement of it, that each time we do not naively choose the lowest and cut it, we choose the lowest basically when it's degree 3. And if it's not degree 3, if the lowest is degree 4, we'll choose the lowest degree 3. Because we want to avoid cutting degree 4, so we just choose lowest degree 3. And this gives the description of our first algorithm called up. And let me define here. Is the following. So each time, so assume, let's say, so if m has any degree 2, then cut it, always cut it. So cutting degree 2 is kind of a basic operation. I mean, there is no choice because you can never allow anything degree 1. So if there is degree 2, then you need to cut it, like no matter what. So this is, but it's always a kind of like a kind of implicit case. Like if we have any degree 2, we always cut it until there is no more degree 2. Now the real thing that where we do have a choice is when there are only degree 3 and degree 4. Okay? So now choose the lowest degree 3 atom, say n. Okay, so this n is the lowest among degree 3. It may not be lowest, in the whole molecule, but it's lowest among degree 3. Let Sn be the set of descendants of n. So descendants need to keep taking children. So we'll show you example later, but descendants keep taking children. And know that every atom in Sn minus n must have degree 4. The reason is, if there's anything in Sn minus n not degree 4, it will be degree 3, and then n will not be lowest. There will be something lower than n. And then we cut all atoms in Sn, starting from n, from high to low.
I think descendants mean nodes above or below.
Descendants means nodes below. So yeah. So child is below self. Parent is above self. Okay. Then choose next. Low is degree 3 and 1 and repeat. Okay. So let me show you some examples. Okay. So let's see. We can do the classic example like. These algorithms, they are not just restricted to the two-layer case, so we are not explicitly drawing the two-layer case. We'll apply it to two-layer case eventually, but let's say this. Okay. So now what do we do? So in the beginning there is no degree 2, we don't do anything. Okay, and then okay, so there is one remark I want to make, but after I explain this. So now we choose the lowest degree 3. In the beginning there is no degree 3, we choose the lowest degree 4. So let me say, or lowest degree 4 if no degree 3. Choose the lowest degree 4, let's say this one, okay? We cut it. And of course, n is here, and Sn is just n itself. It has no descendant. So n is this. And then we cut it, and we get essentially okay. And then we have maybe let's just do the operation here. We cut n. We get this. Okay, so we have a degree 4 here. Okay, so then you see after cutting n, we get 2 degree 3. This is degree 3, this is degree 3, and both are lowest. Both are lowest degree 3s. So we can choose either of them and do the cutting. So let's say we can choose this one. We can choose. There's a choice we can make. So this algorithm is not a unique algorithm. You have a choice to make it at every step, and it's important actually to make some clever choices here. But we'll make a kind of a non-clever choice. So let's say we choose this one. This is lowest degree 3, and we cut it. We cut it, fine, and we get a degree 3 here. Okay? So now, you see, after doing this, what are degree 3 here? This is degree 3, this is degree 3, this is degree 3. So this is lowest, this is lowest, this is not lowest because it's a parent of this. So we can choose to cut either this one or this one. Okay, so let's say we choose cut this one. Again, this is a not clever choice. I'm showing you that this algorithm up along is not going to always work. Let's say we choose this one. We cut another degree 3. Well. And now we have this degree 3, this. The lowest are this and this. Let's say we cut this. So now we only have one lowest degree 3, which is this one. But then you see this one is connected to this one, which is another degree 3. So, instead of cutting this alone, we would like to cut these two together at a 3-3. At a 3-3 because then we want to gain. So we can cut, let me say we can cut this, and then, okay, so if we have a 3-3, a choice of 3, a possibility of 3-3, if we have a chance of 3-3, then cut it. Okay, so this is just remarks to this algorithm. So let's say here we have lowest 3-3, but it's part of 3-3, so then we can cut it. And cut these together. And now this guy has degree 2. At degree 2, we should cut it. Okay? Degree 2. And we cut this, and this out again become degree 2. Okay, so this is an example of the algorithm up. Okay, and see what we get. Okay, so what we can summarize, we can conclude about this algorithm up is the following. That remember our three goals, that we want to preserve monotonicity, that is we want to avoid these bad degree 2s, we want to minimize the number of degree 4s, we want to maximize the number of 3 components. So what happens here is that we preserve monotonicity, which is good. That we do minimize number of degree 4. Well, this 1 degree 4 is unavoidable because in the very beginning, everything is degree 4. So you cannot cut degree 3, you have to cut degree 4. But this minimizes, you only have 1. However, we may not maximize degree 3. So this is a problem we still need to solve. But again, you see, by doing this up algorithm, it already provides a way to avoid loss, avoid degree 4, to prove monotonicity. So the only thing is that we need to get enough 3. So this thing, if we are not clever enough in the choice of the cuttings we make, we may not maximize the number of 3. Okay, so before we end, let me just show you what we really should do, like in the case just now, how to maximize the number of 3 is this. Should do is that we start by cutting this lowest. Fine, we cut this. Okay, and then we generate 2 degree 3s. This guy. I should draw this in here. Okay, we should cut this one instead of this one. Of course, it is not specified in the algorithm up, so we don't know. So if we are we have bad luck, okay, no, we are not clever enough, we may miss this. But the real thing is that we should cut this instead of this. So let's say we cut this. Then what happens is that we get degree 3. But then the lowest degree 3 would be this one. So this is not lowest, this is parent of this. But then this is degree 3, this is degree 3, they are connected, so then we get a 3. We can cut them together. And again, we get a 3. And this is the lowest degree 3. We can cut them together. We get another degree 3. And then finally, we cut these together. This is the lowest degree 3. This is degree 3. And then we get another 3. Then we get a number of 3's equals 3 instead of 1. And we are good. Of course, I mean this cannot be deduced from the up. We still need to make some clever choices, in the algorithm up. So we need more work. So the idea is that the idea for the rest of the essential for tomorrow. In some cases, under some assumptions of the graph, we can make clever choices, essential clever choices in up or its variance to maximize 3. and then we'll be good. Okay, so there is a large class of molecules, and for these molecules satisfying some properties, we can specifically make these clever choices, and so that we do maximize the number of degrees free. So we'll see examples tomorrow. And in other cases, there might be really bad cases, and that when you just apply up, no matter how you make the choice, you're never going to get enough 3, 3. There are possibly such graphs, and in other cases, we'll need to combine up with other algorithms. Essentially, there is one other algorithm, which is essentially the kind of the greedy algorithm which we'll talk tomorrow. And in the other case, you'll need to combine the up with other algorithm to get the 3, 3. Okay. So you see, today we just discussed this basic algorithm. So it already kind of meets 2 of our 3 requirements. And then for the final one, we still need more work. And that is something we'll be discussing tomorrow. So we'll make assumptions. If the molecule satisfies condition A, then we can do this. If not, it satisfies condition B, we can do something else. If really not, we satisfy condition C, then we'll try to use some other algorithms to close. Okay, so I think that's it for today. Yes. This factor is important to cancel this C to M factor coming from common
But
parts.
C to M, I think C could depend on the number of layers.
No, C doesn't. C doesn't depend on the number of
But
layers.
the partition is not atoms into.
No, you see, C is 10, or C is 10, because if you look at the construction here, C only depends on the number of trees in each layer, and number of trees is bounded by 10 to the power of the number of atoms, and this only comes, and everything else comes into the row part. Yeah, I forgot to say, C is the actual constant that does not depend on the number of layers.
And what is the desired magnitude of row that you have in your mind?
The row is anything. Row is a number of UD connect. Row is anything. So the row is the maximum of these crossings. The total number of crossings. So it can be as small as 1. It can be as large as the size of a molecule. But no matter what, you always have this bound.
If there's no more question, let's thank Dong Yue.